All right, in this video, we're going to focus on finding relative extrema. We talked about absolute extrema using the EVT, the extreme value theorem, a few videos ago. Today, we're going to look at using something called first derivative test. So to kind of show you the motivation, or at least the backstory here, let's suppose that we have a blank grid here. We have a blank XY coordinate system. Hypothetical, let's say I don't know a function. I don't know what its graph is, but I know things about the function. So supposing at -2, let's say that I know for a fact that my function is increasing to the left of -2. I don't know what it looks like, but I know that it's increasing. And to the right of -2, I know that my function is decreasing. Furthermore, I know at x equals -2, I have a horizontal tangent. If I was to ask you, given all of this information, just sort of sketch any kind of graph that you would think matches all of these descriptions, you would probably draw something kind of like this. And then if I was to ask you, what do you think is happening at x equals -2? It seems reasonable to make the conclusion that you're going to have a maximum at -2 because I went from going up, stopping, and then going down. Obviously, assuming that you have continuity. Now, if I kind of flip that around, also at x equals -2, if I know I was decreasing and then I started increasing, and I have a horizontal tangent still at -2, and I said, graph what you think is happening, it seems reasonable you would graph something like this. In other words, you would make the conclusion that you've got to have a minimum at x equals -2. This is basically the first derivative test. Not in the same order, but that's essentially what we're doing with the first derivative test. We're checking increasing, decreasing, and when we have horizontal tangents, or in some cases when the tangent doesn't exist, when you don't have a derivative. So the question you might have is, well, how would I know if my function is increasing or decreasing? That all has to do with your derivative. The derivative tells us the instantaneous rate of change at a point. What that means is if I have a positive derivative at a point, then my function is increasing. If I have a negative derivative at a point, my function has to be decreasing. Now, we're not going to be able to check every single point in the domain of our function or the domain of the derivative, but we can always make a comparison with the number 0. If I know when I have equal to 0, or I should say this, if I have a real number, which is a value of a function, then that real number I can either compare being equal to 0, being bigger than 0, or being less than 0. So the trick is we're going to check when we have equal to 0 and then test things near to there. The results will either be positive or negative, kind of like in pre-calculus when you had the zeros of a function or the x-intercepts and you were trying to figure out if the graph of that polynomial went above or below the x-axis. Same idea. So that kind of spells out the steps of the first derivative test. Let me put that in writing here. So what we're going to do is first find the critical numbers. So you should remember that means find derivative set equal to 0, and also figure out when derivative is undefined. So any of those numbers are critical numbers. Next, you're going to do a sign analysis of the derivative. That's actually really important. You're not doing it with the original function. You're doing this with the derivative because you're checking positive to mean increasing, negative to mean decreasing, and that all has to do with your derivative. Once you do all of that work, you're going to make the correct conclusion. Meaning if you went from increasing to decreasing, you must have a maximum. If you went from decreasing to increasing, you must have a minimum, obviously assuming that you have continuity. What I mean by that is you can get critical numbers when you check you have, say, increase to decrease. But that critical number might be a vertical asymptote of your original function. That's not a point on your graph. So what I'm getting at is once you do this, you still want to check to make sure that the physical points on your graph exist. They're not points of discontinuity. So as a quick example here, let's say I have this cubic polynomial. Go ahead and pause the video, give this one a try, going through all of these steps and see if you can find the relative extrema. And in 3, 2, 1, I'll tell you the solution here. So take my derivative, set that derivative equal to 0. I get two critical numbers. Do the sign analysis near to them. So around 0 and 1, I want to test numbers to the left and to the right of each of them. So I test them in the derivative. Looks like to the left of 0, I get a positive derivative. To the right of 0, I get a negative derivative. And then to the right of 1, I get a positive derivative. So that means my function was increasing, and then it decreased, and then it increased. So that means at 0, I must have a maximum. So to find the actual y value, I can plug in. And then at 1, I have a minimum. And these are relative extrema because I don't have a closed interval. In some cases, we know we can find absolute ones, like for even degree polynomials, but this is really focusing on finding relative. That should give you more than enough information to get those questions answered on Schoology.